So I guess it's time to start. My name is Sergey Tarima, and I've been with the MCW since 2005. I work in the Division of Biostatistics, and once in a while...
Progress.
Hello?
Hello?
Okay. So, and once in a while, I work with EHR data. So, and today we will talk about the defining your outcomes when you have like a research question. So what your outcomes are going to be. Let me see what I need to click on next. Okay, so in total, I have like 27 slides in my presentation, but a few of these slides, they are mostly administrative. So like first 7 slides are administrative. And then we have about 20 slides where I talk about outcomes, defining outcomes, what outcomes, what issues we have with outcomes, and how to solve these issues. So on second slide, we have some information about our biostatistics, epidemiology, and research design core of CTSI, and our director, Spencer from UWM. And support is provided through 3 locations: UWM, our Division of Biostatistics Consulting Service, and CAPS. So if you want to get biostatistical consulting help, so you can apply for mini grant awards. And typically, if you receive this award, you get like 4 to 6 hours of biostatistical support. Usually, it's not much time, right? So, but mostly we discuss project aims, study design, how to formalize your research question. So we can read a statistical analysis plan which you prepared. We can perform some sample size calculations. And if you have some preliminary data for your proposal, so we can take this preliminary data and do some preliminary analysis to extract quantities we need for sample size calculation, for example. This is what is typically done within like 4 to 6 hours. If some more data analysis is involved, so potentially you can get like extension to this 4 to 6 hours. You can apply for mini grant again. So, and you can get like a few more hours, maybe like around 5 hours or so. But even if this, like 2 chunks of 4 to 6 hours is not sufficient for your research question, you can apply to our biostatistical consulting services, but that will be a separate fees. Biostatistical consulting services. So what we provide here from our Division of Biostatistics, we provide a lot of data analysis in addition and beyond to what is provided by these mini grants from CTSI. So we can extend on CTSI, on sample size determination. So we work on grant proposals with investigators. So perform plenty of different data analysis, like modeling, design of clinical trials, because like design of clinical trials sometimes involves substantial like Monte Carlo simulations, and 4 to 6 hours might not be enough to do that. So here we have some basic information for biostatistical consulting services from administrative and how expensive our services are. PhD, 1 hour will be 165 hours. A data analyst with a master's degree in statistics, it's 100 hours. And for outside clients, rates are higher, but you need to get separately in touch with our administration. So, and this is the email address you can use. But in addition to this fee for service, we also have like integration contracts with different departments and divisions within MCW and neighboring institutions. If you have an integration contract, so in this case, you can just submit an iLab application, and this is the link how you can get access to these applications. Our lecture series. So my lecture, it's lecture number 3 in a series of 4 lectures, how to work with EHR data, electronic health records. So first, Dr. Ruta Brazauskas talked about observational studies in general. Then more specifically, Dr. Zabo in April, like a month ago, talked about defining the study cohort. So, and she talked about like ICD codes, how these ICD codes can be used to determine your inclusion and exclusion criteria and to determine your cohort. And I will be talking further how to define your study outcomes. And our final lecture will be done in a month by Spencer Huang on creating analytic data set for data analysis. Objective of this of today's presentation will be just to understand importance of carefully defining study outcomes. Then we will go over typical problems associated with defining study outcomes, and we will use 3 examples. A couple of these examples are artificial, but still based on my practice, and one real-life study which I worked with a couple of investigators from the MCW. And in the end, so like our example number 3, we will also talk about difference between observable and counterfactual outcomes. Let's talk a little bit about a research question. What research question is? So research question, it's like this is where you start. So, and it's very important to be careful how you prepare your research question, because in many cases when I talk with investigators, research question is not clearly defined before we come to meet with the biostatistician. And in many cases, investigators already collected some data, and only after that, only on the basis of their data, they try to identify what the research question is. So it's kind of a little bit out of order. Not a little bit, it's out of order. So then you define the research question. Typically, you have to go through a literature review and describe the importance, or maybe at least pay attention to the importance of your research question and the impact. And this is what you typically see in grant submissions, right? So these are the sections from grant proposals. But somehow then people come to us in many cases. These 3 components are not really carefully so investigators do not spend much time on these typically. So research question need to be further formulated in some mathematical statistical terms, because this is how we statisticians think. So, and in many cases, you just have a research question and you need to identify clearly what our exposure variable is, what our outcome variable is. And if there is no exposure and outcome, suppose it's just study where you want to investigate correlations between 2 variables, because there is no like causal. So, and sometimes you just need to clarify what your variables are. So it's not necessarily X and Y, exposure and outcome. Sometimes it's just X1 and X2. So, and statisticians, when they see research questions, statisticians think how to formulate all the components which you see within the research question in terms of statistical variables which we can analyze, in terms of like columns within our data. And when you collect data, we typically think about a rectangular data set, like a table, so where we have columns and rows. So this is a typical starting point for data analysis for a statistician, a rectangular table. And when we formulate exposure and outcome, so or whatever variables are, sometimes we just add additional columns to our data set. Someone is not muted. Let me just mute. Yep, okay. I can mute some people. Good. Now, and the 3 examples which like 2 groups of statistical methods. When statisticians see the data, so, and if they have a research question, so in this case, next step is to think about a statistical analysis plan, how this data should be analyzed. And in statistics, there are statistical methods developed for two big chunks of groups of analysis. So it's estimation and hypothesis testing. And down below, I have a few examples which we will go over in my presentation. So first example, it will be evaluate association between age and pain. So in this case, I do not have like a separately X and Y. Like I do not establish a causal association here. I'm not claiming a causal association because this is just an association. For example, which can be measured by a correlation coefficient, either Spearman correlation coefficient or a Pearson correlation coefficient. So that will be estimation task, and you estimate correlation. Now, hypothesis testing task is, suppose you want to test whether this correlation coefficient is different from 0 or not. So then it will be like a second task. And we will go through both an estimation and hypothesis testing. Example 2, in this case, we will look at changes in BMI before and after a bariatric surgery. So, and I think a while ago, I had a study related to this, and we kind of spent some time to determine what our outcomes were. So, and that's why I felt like that will be another artificial study, which essentially is based on a real life consulting project, which I had. And our last example would be to compare effects of COVID and flu vaccines on rates of new diagnosis of immune diseases. And this is an ongoing project with Mike Putman and a couple of students from the MCW. Okay, example 1, association between age and pain. So age, just easy, right? So we have some ages measured over time, like for each patient, we have an age, right? But pain is typically measured on multiple days. For example, it depends on the study, right? So if you're talking about a cross-sectional study, so in this case, we have just single pain measurement. But if we have data over time, so in this case, potentially we can have multiple measurements. And possibly these measurements are not equally spaced. So in this case, it's kind of difficult. For example, suppose we look at 7 days of data, but we have only first assessment on day 1, but after that, pain measurements are done like on days 8, 10, etc., etc. So, and there are different ways how this pain data can be quantified, can be summarized at patient level into a single number, into a single outcome. But this is what statisticians will be looking for just for one number, how to identify your outcome, which you will be analyzing. But in this example, I'm not even focusing on pain because behind pain, there are a lot of different outcomes which you can formulate, right? But even for age, I would just consider like 2 possibilities how we can determine age. So age as an option 1, so it will be like age at admission. Suppose a patient was admitted to a hospital, right? And over time, we do have pain evaluations. So pain evaluations, I would just say, okay, I will just summarize first week of pain observations and just consider average, okay? Average. But it's not necessarily the best way to do it. It's just one possible option. But for age, just age at admission, just one option. So how would we typically analyze data if we have age and pain, 2 continuous outcomes? Well, we typically want to quantify how these 2 variables are associated with each other. And Spearman correlation coefficient is a reasonable quantity because Spearman correlation coefficient describes association, a monotone association between 2 continuous variables. Spearman correlation is different from so-called Pearson correlation coefficient, right? Because in Pearson correlation coefficient, we are evaluating whether there is a linear relationship between our 2 variables, age and pain, 2 continuous variables. But Spearman correlation coefficient, instead of looking at actual ages, it just looks at ranks, right? So for example, if we have like 30 people, right, and here we have their ages from, like in this slide, we have like from 30 to 70 years of age, right? So that will be our range. But instead of looking at their actual ranges, we would say the youngest one, the second youngest, the third youngest, etc., 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 to the oldest individual. So in this case, we're looking at ranks. So instead of actual numbers, we will just place their ranks 1, 2, 3, 4 up to 30. Okay, and in the same manner, we convert our pain data also into ordinal scale, like 1 through 30. Okay, there are some issues associated with this approach because there are some possibly ties. Specifically, when we're talking about pain, and pain is typically measured between like 0 and 10, is discrete scale, like 1 through 10, right? Yeah, but nice part about Spearman correlation coefficient, because it captures monotone association, okay? So how do we analyze Spearman correlation coefficient? One option will be to apply so-called Fisher-Z transformation. And Fisher-Z transformation can be applied to Pearson correlation coefficients and to Spearman correlation coefficient. And the overall idea is that our correlation coefficients are quantities between -1 and 1, like bounded quantities, right? But when we apply Fisher-Z transformation, our data, when we receive our data, so we do not have these two boundaries, -1 and 1. If you look at the distribution of a correlation coefficient, typically we see, so for example, if we have like a lot highly correlated data, right? So then we see, like, if you look at a histogram, so histogram would be skewed toward 1. If we have negatively correlated data, then the histogram would be skewed toward -1. So we have skewed data. But when we apply Fisher-Z transformation, our data become typically, not always, typically approximately normally distributed. Okay, so, and this is so-called a transformation, after which we apply a Z-test. And typically, if sample size is around 30 or larger, so we can rely on asymptotic normality and we can apply Z-test. So what is happening in this example, if we just look at the correlation, right? Spearman correlation, so p-value is equal to 0.04. But in this case, we use a continuous measure for our outcome age, continuous age. On the next slide, I use a different definition for age. So I use categorization, because you remember, like, our range for the data was between 30 to 70. And why don't I slice it somewhere in between, like 45 years of age? So in this case, I'm losing some information. So this is what statisticians typically don't like, right? So in this case, if you have a categorical age, so, but that's a pretty often this is done. So for example, if you look at medical literature, and sometimes age is considered to be as a continuous predictor, right? But sometimes it's considered as a categorical predictor with some ranges, like, I don't know, under 18, for example, right? So let's say 18 to 25, 25 to 35, etc. Because it's easier to explain in the manuscript. But from statistical perspective, you lose information. So, and in this case, if we use a different definition of our variable age, different quantification of age, and here I say have option 2, we cannot look at scatter plots anymore. But typically, if we have a binary variable, age right now, like younger and older, right, above 45 or below, so then we have one continuous measurement. Pain can be viewed as a continuous measurement, right? Even though it's still ordinal and still there is a discrete scale behind. And the age variable is binary. So to describe association between these two variables, so we cannot use scatter plots anymore, but we can use box plots. So, and that's why I prepared box plots here. And how do we test association between these two variables? Pretty often, Wilcoxon-Mann-Whitney test is used, okay? Because previously we used like Fisher-Z transformation, right? And a Z-test. But in this case, we use Wilcoxon-Mann-Whitney test. And p-value right now is 51%. So it's not statistically significant. And that will be an example where different definitions for our variables, okay, lead to different quantification of association and different descriptions of our association and different tests and different p-values. Okay. So that was like two different ways how we can quantify age. It's like two different definitions. And statisticians, then they see a research question. Our research question was, we just wanted to look at association between age and pain, right? But what is age and what is pain is important for statisticians, because this needs to be clearly defined, how we define age and how we define pain. I decided not to talk about pain because in pain, it's just so many possibilities how we can quantify pain. A few conclusions from this example number one. Different definitions of variables might lead to changes in interpretation of findings, to graphical representations, and we'll have underlying different power properties. And we will be using different statistical methods if we use different definitions for the variables. Okay. But ultimately, suppose our objective would be just to look at association, whether association exists or doesn't exist. And actually, both tests, which I have prepared, they look at association. Okay, they just look at different quantities, how we quantify our age variable leads to different statistical tests and certainly to different power properties. Why clear definitions of all variables is important? Okay, so you remember I mentioned like two big statistical tasks we typically work with: hypothesis testing and estimation tasks, right? There are some other statistical tasks like prediction, classification, diagnostics, so I'm not talking about those, but these are two most prevalent ones: hypothesis testing and estimation we deal with. So in hypothesis testing, statisticians typically worry about type 1 error and power. So, and if we do not have a clear definition upfront for our suppose age variable, so in this case, there is uncertainty what type 1 error is. And if it is an uncertainty, what does it mean? It means that if we did not clearly say what age is, so later on, potentially, a statistician or an investigator can propose different definitions for age. What it leads to? It leads to different statistical tests to be performed. So suppose we just tried continuous age, then we tried categorical age, then we didn't like it. Suppose we applied some transformations to our pain variable, so we can view pain variable from different perspectives as well, so we can quantify it differently. So, and what is happening? We perform multiple different tests of association between age and pain. So we're looking at association from different points of view, right? And this is an example where we cannot really control type 1 error, because type 1 error is a probability we make a false claim of association than it doesn't really exist, right? But the more different tests you do, more likely you would find this association. So, and if you did not predetermine upfront how many tests you're going to do, in this case, you can easily go into a fishing expedition, explore all of these different associations between these two variables, and eventually, possibly, you can find something, okay? Yeah, and I mentioned that interpretation of findings for different definitions of variables will be different. Another problem we often see is that when we have like subgroup analysis, okay? So that's the recipe of disaster for disaster. So if initially you plan to look at association between, say, age, right, and pain, for example, but somehow later you did not find a significant result, right? So researchers come to me again. So p-values are not significant. Can we look at subgroups, for example, by gender, right? So like males, one analysis, females, another analysis, like zodiac signs, a few more analysis. So this is what we try to avoid. So that's why it's important to have pre-planned analysis. And pre-planned analysis means that everything is clearly described before you actually looking into the data, before you start analyzing your data. And if you planned properly, in this case, good planning typically involves good control of type 1 error and power. Now, estimation problems. When we're talking about estimation, we do not do testing typically, right? So estimation, in estimation, we're looking at quality of estimation. For example, we're looking at standard errors, right? Looking at confidence intervals. We're looking at biases, whether we have bias or not. But if you want to estimate these important quantities like bias or standard deviation, So we need to have a clear definition what we are actually estimating. If there is no clear definition, so in this case, these two most important quantities, which I listed over here, bias and standard deviation, they just not defined. Okay. So I kind of criticized these multiple definitions, right? But at the same time, multiple definition is still possible. But all of these multiple definitions for your variables need to be clearly described before you start analyzing the data. As it could be kind of, this is the best case scenario. So you probably want to justify why you use different definitions from a clinical perspective, but also from a statistical perspective. We should be able to control like type 1 and type 2 error, for example, right? So, and that's why we need to say how we adjust for multiple comparisons. You heard probably this done-it adjustment, Bonferroni adjustment for multiple comparisons. Okay. That was my first example. Second example, to evaluate changes in BMI before and after a surgery, a bariatric surgery. So when they have a research question, they typically define our population, right? And population is determined by our inclusion and exclusion criteria. This is what Dr. Szabo covered last time. In our case, initially, bariatric surgery patients, that will be our population, right? In EHR, for example, we can say, okay, so bariatric surgery, they have an ICD code 10, so it will be Z9884, bingo. So we just pick these patients who had this bariatric surgery. And typically, when you extract data from EHR, you need to determine time frame, right? So specific period, for example, from January 2015 till the end of 2022. That will be the data which we extract. And our objective would be just to evaluate changes before and after the bariatric surgery. And now we go into details. What does it mean before? What does it mean after? Let me just go to the next slide. So in this case, we just talk about before. How we can define a BMI before a bariatric surgery. This is what statisticians have to deal with, right? So it's easy to write BMI before bariatric surgery, right? But what does it mean? And here I gave just 4 possible options. A closest BMI to the surgery date, okay? So in this case, from time zero, it will be our bariatric surgery. So we're going back, right? So it will be the closest BMI assessment, BMI value. Another possibility, the closest BMI date, but excluding pre-surgery fasting period. Because right before bariatric surgery, it is recommended to go fasting. So in this case, like weight goes down, right? I don't know how long they fast, maybe like a week or I don't know. But yeah, weight goes down, BMI goes down. So in this case, it's a very different baseline. If you compare something like from negative 2 weeks and even further into the past, as compared to like the closest to time zero assessment of BMI. Or, for example, you can consider another possibility, like the highest BMI in a year prior to surgery, right? So this is like your starting point, and you want to compare how much you improved as compared to the whole year before the surgery. Or you can consider average BMI, just 4 possible options. Suppose like clinical decision was made. So we can look at one of these components, right? Excuse me, one of these definitions. So we kind of clarified what our definition is and how we want to look at pre-bariatric surgery BMI. Now we look at the data. And then we look at the data. So data also dictate what is actually feasible to estimate on the basis of the data, and some other things are showing up. But before we got the data, how we got the data? So typically we use something like Trinetics or I2B2 to discover a cohort of patients, right? So in this case, we identified which patients we are interested in, which fit to our inclusion criteria. I just listed, ICD code and time frame. So we extracted patient IDs. Next step, we submit these patient IDs to the honest broker tool and download a database. So database can be relatively big. For example, suppose we just downloaded not bunch of CSV files. That would be like one option that you can download. But suppose we downloaded an SQL database, and we call it mydatabase.db. Suppose we have a single file, maybe 5 gigabytes, for example. Okay. In this database, there are many different tables inside. And one of these tables will be of a particular interest for us, table vitals. So in this vitals table, we have this BMI data evaluated for each patient, and they also evaluated over time. So multiple assessment of BMI for the same patient. Here I added, so for those who are interested, R code, which can be used to read the data in from external data file, and just to create an R object vitals with this specific table where BMI data is actually contained. So let me just describe to you what we have here. So first line, library. So I just attach a library in my R code. Then set WD, I define what my working directory is. So, and that's my Linux computer at home. Next one, we need to define our database driver. So that will be SQLite, because I know that my database is in SQLite format. So, and that's why I will be using this driver. In next line, I define what the name of the file, and then I establish a connection using dbconnect command. So I will use this driver to establish connection with my database, with my SQL database. Then next step, I just, submit the command db list tables, because within this file, within this db file, SQL file, there are multiple tables and they are all interconnected. And I just want to see what the tables are. And out of, say, 20 tables, I'm only one table which I'm specifically interested in, table vitals. And next step, I just create a data set within our environment, which is called vitals. That will be a data set, essentially a rectangular data set, a table, which I can work with as a statistician, because statisticians like tables. And that will be an example of this table. So I just, because this is a de-identifier data set, and I extracted a few lines, so for you to see. And it's nice part about this honest broker tool, because you get and Trinetics, the whole tandem how we work together, because you get the identified data in the end. So we got fake patient IDs, fake encounter IDs, like a second column. Third column, it will be date, which is shifted. Within each patient, there is a shift plus minus 10 days, which is never equal to 0. And the next 3 columns will be most interesting to us, because what we are interested in BMI, right? And BMI is calculated on the basis of patient height and weight. So I can use height and weight to calculate BMI. But sometimes, for example, only weight is available, and then I have missing BMI. So these type of situations, we did not really originally think of, right? So when we just talked about clinical definition of our outcome. Now, but sometimes we do have evaluated BMI, even though height is not available. So what had happened? Most likely, a previous patient height was used, right? Because, well, patient height typically does not change unless we're talking about children, But for example, here we're looking at like only 4 days apart. There are 2 assessments, right? So yeah, and BMI changed a little bit, so went down slightly. So probably previous height was used to calculate his BMI. And here we have some other vital measurements. Many ways to define BMI after a bariatric surgery as well. So what does it mean, BMI after bariatric surgery? So you can look like 1 month ahead, 6 months ahead. And here I gave like a few options, like 12 months, 24 months ahead. So all of this associated with different definitions, right? So suppose we just choose, okay, we will look at 24 months, but how likely you have BMI evaluated 24 months after the bariatric surgery? Highly unlikely. So that's why we have to, to consider like a window around it, say plus minus 1 month. Typically not enough, because if you look at the data, how many patients would have a BMI assessment within 2 months window, right? maybe like 5%, I don't know, 10%. So it's drastically reduce your sample size. Suppose we consider plus minus 6 months, right? In this case, maybe we get like 60% of patients who have at least one BMI assessment within plus minus 6 months. Suppose we choose this one, plus minus 6 months, it's like 1 year window, right? But again, so we still have to make some further decisions because some people have multiple assessments, some just single assessment. So, and here we also have some options how we can assess what would be the value at 24 months, the BMI value at 24 months. One option would be just to pick a closest BMI assessment, or another possibility would be just to apply like a linear trend, like just predict using linear trend, just predict what is happening, what would be the value of BMI at 24 months. So in this case, this assessment comes with some uncertainty, which is typically ignored. So when we define our outcomes in this manner, yeah, but this is what we did just to identify single outcome, which would be change in BMI between before and after bariatric surgery, right? So because there are plenty of different possibilities, but what statisticians typically need for planned data analysis, we need to have a clear definition. Okay. What else can we say after looking at the vitals data? Some patients might not have BMI measurements at all within a pre-specified window. Okay. So what happens in this case? If before BMI is missing in the way how we defined, if after BMI is missing in the way how we defined it, we got missing data, right? How to handle missing data? That can also be planned. So in this case, we are talking about a planned statistical analysis already, right? Because it's linked to our outcomes. Or another possibility, we can say, we will just exclude these patients, right? Who did not have BMI measurements. Exclude, which means we are modifying our exclusion criteria, right? So in this case, we are talking about a different patient population. So we are talking about patient populations who are in care, who are pretty often attend their appointments, right? And the findings can be very different if we consider the whole population. And here I mentioned a few ways how we can deal with missing data. So one option would be to use some missing data approaches. For example, if like what we saw, if weight is available, so in this case, and if we assume that height doesn't change, so in this case, we can use height from previous, from before, or from after. So it doesn't really matter because we're looking at retrospective data, because it's a retrospective data analysis. It's not like forward data collection. It's not a prospective data collection. So, and we can impute what would be a realistic, realistic weight. But again, sometimes both height and weight are missing. So in this case, it's probably unrealistic to plug in some reasonable value. Some conclusions from our example number 2. Original research question might be not feasible. So in this case, we don't know how many percent people have missing, what percent of patients would have missing like before and after BMI. So, and again, so potentially we can even go back and to reevaluate what our inclusion and exclusion criteria are. So how we can mitigate these issues upfront in the beginning? So one option would be to proceed like a two-stage procedure. So for example, suppose we have like a pilot first, like small pilot study, and then we redefine our study outcomes on the basis of this initial look into the data. But there is a danger here, because in many cases, if you look into the data, we potentially can change our research question in the favor of our hypothesis. Okay. For example, if you see the data initially, you can reformulate your hypothesis. So in this case, it's more likely to be proved. Okay, I'm talking about your research hypothesis to be proved. Statistically, this means that our null hypothesis will be rejected. So that's why it's a danger when you're looking into the data. So how to avoid this, impact of early peeking into the data. So potentially you can have like an independent statistician, right? So you can ask independent statistician to look into the data and specifically look at rates of missing data, how many VMIs are available, within what time periods, without specifically looking into your research question. Suppose your research question, suppose you want to consider like two groups of patients, right? Want to compare two groups of patients. If a statistician or maybe US researcher is blinded to this two group allocation, right? This specific column. So in this case, potentially you are not influencing your research question, okay? Example number three. So that will be joint work with Mike Putman and a couple of students. So objective would be to compare new diagnosis of immune diseases. So we had two groups, COVID, and we had the flu vaccine group, which will be control group. So we defined our observable outcome. It will be 6-week incidence of our new diagnosis for immune diseases. And this is the data which we downloaded from, not directly from our CTSI CRDW database, right? But from a large database from Trinetic itself. So like CTSI only has access like to Froedtert and Children's Hospital, but Trinetics, they have like 60 or 70 like big healthcare systems, hospitals. So it's about 70 locations. And we downloaded it about 200 gigabytes of data. And it was like a zip file, big zip file. And then I unpacked this zip file. It was about close to a terabyte of data. So then I had to install like a SQL server on my computer. I purchased external hard drive to keep this data. And Mike Putman, he actually very proficient in this big data analysis. So he suggests that right now you can use RCC resources just to download these huge data sets directly into their into RCC account, and then you can directly work with it. So it's much more efficient than working on your personal computer. So comparing effects of flu and COVID vaccines, observable outcomes. So we had like 15 different immune diseases. So what we've done, we identified, because immune diseases, so it's like ICD code, right? And we have multiple of these ICD codes over time. So what we did, we just looked at the first one. So and we said, okay, there are some limitations with this approach. But when we choose the first one, and in this case, we say, okay, that will be the date of diagnosis of this disease. Okay. Now we have like 15 different diseases, immune diseases. So next step, we aggregated them into larger groups. So we had 3 groups in total. So, and for each group, like first occurrence of a diagnosis within each group, that will be like a diagnosis within each group. So this is how we identified our outcomes. And we looked only at those who did not have any immune diseases before vaccinations. So we had like 2 vaccinations, flu versus COVID, 2 groups. Okay. So that will be our observable outcomes. But observable outcomes sometimes do not allow us to evaluate, for example, impact of COVID versus flu vaccines, right? Because it's observational data. So if you really want to evaluate like one treatment versus another, you typically want to have a clinical trial, right? But you cannot do it in observational studies. But there is an approach which allow us to look at a pseudo experiment, okay? What would have happened, for example, if you would have a randomization between 2 groups? Because initially, if there is no randomization between 2 groups, right? If it's not a randomized clinical trial, our groups can be different. For example, like flu and COVID groups, they can have different demographic profiles, right? So, and flu vaccine is typically, people get flu vaccines during like flu season, right before flu season. But COVID vaccine happened, when it came to the market, when it's available, and it became available from like Pfizer and Moderna pharmaceutical companies. So, but one option would be to consider so-called counterfactual outcomes, the outcomes which you do not really measure in real life. So, for example, one counterfactual outcome will be, what if everyone in your population receive a COVID vaccine, right? In your sample, receive a COVID vaccine. Or another counterfactual outcome, what if everyone in your sample receive a flu vaccine, okay? So, and that would be, and here we have a table, and I try to illustrate the difference between observable outcomes and counterfactual outcomes. So I just generated 7 patients, right? With some age, some gender, some employment data, right? And vaccination status. So patient received in my data are the flu or COVID vaccine, right? And like green column, so that would be my observable outcome. So for each patient, I know whether like within 6 weeks after vaccination, they received or didn't receive an immune disease, okay? So, but there are 2 extra columns here to the right. So these are potential outcomes. So in this case, if person really received a flu vaccine, right? So I know the outcome. So it was 0, no immune disease. But if this patient received COVID vaccine, I don't know what would have happened to this patient if this patient would receive a flu vaccine. So that's why I put a question mark here. So, and this is what is happening. So if patient received a specific treatment, I know the outcome. If treatment was not received, I don't know the outcome. But the assumption that the outcome actually exists in counterfactual world. Okay, so this is what the counterfactual outcome is. So let's look at this data, COVID versus flu vaccines. So because it's observational data, and we can look at 2 columns, like flu vaccine and any mRNA, okay? So, and mRNA vaccines were actually determined on some specific medication ingredient, which was part of both Pfizer and Moderna vaccines. So that's why we kind of lump them together. So if you look at these 2 groups, we see some really big discrepancies sometimes. For example, in mRNA group, right? So we had close to 1 million people, and influenza, we had more than 1,000 people. But that was a subgroup from our original sample of 3.8 million patients, because we wanted to look only at those who actually in care, because those, and we defined in care, it's like to have at least 10 encounters within healthcare system 2 years prior to vaccination. So, and what we see some differences. For example, like Hispanic Latino, it will be 7.5% out of those who got mRNA vaccines, right? And only 2.7 among those who got influenza vaccines. So that's why our samples are different in race ethnicity variable. Now, the more drastic differences we see in the timing. You see, it's like in fourth quarter of 2020, very few people, it's like only 4.5% received COVID vaccination, because this is when COVID vaccinations only started rolling out through some states, maybe some locations. But, you know, it's like big chunk of participants received vaccination in first quarter of 2021, then 2022. But, you know, when you look at here, should go back. Yeah, if I look at COVID, if I look at flu vaccines, a lot of them actually got flu vaccinations in fourth quarter of 2020. What I need to have for to be able to compare 2 groups, the groups should be similar. So one option to evaluate what would happen in counterfactual world is to apply so-called inverse probability weighting. Okay, so, and here I described inverse probability weighting. So in this case, for those patients who got COVID vaccine, we would calculate inverse probability weighting, 1 over Q sub I, where Q sub I, it will be probability that this person receives a COVID vaccine. It's based on a separate statistical model. And for those who got flu vaccine, we can also calculate weight. So in this case, it will be 1 over P sub I, where P, it will be probability to receive a flu vaccine for a specific patient. So in this case, for each patient, I can calculate his weights. And then I calculate weighted frequencies, what is happening. You remember what we had before? Total number, like 900,000 people in mRNA group and 100,000 people in another group. So now, after reweighting, I got like 1 million people in one group and 50,000 and 1 million and 50,000 in another group. So almost identical, because I reweighted my cases and imitated the scenario where everyone would get one vaccine or everyone would get another vaccine. So these are counterfactual scenarios. Now let's look at what is happening with, because we saw discrepancy in Hispanic and Latino proportions. Now it's like 7.0 versus 6.8%, almost identical. Now, and similarly, if you look at these quarters, so quarters are also very similar. So this is what is happening. Then we applied reweighting. So we made our groups artificially similar by this reweighting. And we can also look at so-called left plot when we see imbalances before and after weighting, right? So, and if you look at unadjusted analysis before weighting, right? So we see some discrepancy in terms of covariates. So this is where we have like this red, pink dots, right? So, and after the adjustment, so our covariates are much more balanced. So it's over here. Okay. Conclusions. I'm on slide 27, my last slide. Observable outcomes. Observable outcomes are applicable to real-life settings. This is what is happening in real life. And usual statistical methods are applicable. So that would be like regular t-tests, chi-square tests, regression models, etc. But when we're talking about counterfactual outcomes, so we essentially generate hypothetical settings, right? But in this case, we can, I would say, more accurately, more fairly estimate the differences attributed to flu versus COVID vaccines. It's like similar to what would have happened in a randomized clinical trial. So interpretation will be different, definitely as compared to real life settings. As I mentioned, we can mimic what happens in randomized clinical trials, and data analysis is often based on two groups of statistical methods. It will be methods for missing data. Typically, multiple imputation is used for this missing data. You remember when I had these question marks? Or inverse probability weighting can be used as another approach to evaluate what would happen in counterfactual settings. And I'm done. Thank you. We have a few minutes, so if you have any questions, I can try to address them.
Sergey, thank you for that. Question for you. So if you're using a large cohort, like 3 million patients, and you can pulling out, let's say, 2 groups to compare, is it better to pull out the complete cohorts and use counterfactual analysis, adjustment, or to set your criteria so that you can sample each of those groups to have equivalent sample sizes?
Typically, if you sample, you're losing some information. So, and for example, if you want to look at rates of immune diseases, of rare immune diseases, for example, then rates are typically low. And if you, for example, out of 3.8 million patients, if you would select 10,000, for example, you might not have enough power to see the difference. But you will be able to use like regular PC computer to address your research questions. So there are some other designs which allow you so-called case cohort design. So you extract all cases which you have. For example, suppose you got 15,000 new immune diseases within like 6 weeks, right? And you choose a simple random sample of controls. And controls are those who did not get an immune disease within 6 weeks. So that would be another option. So just a simple random sample, typically inefficient. Sometimes it works, sometimes it doesn't, but it's associated with information loss.
Thank you.
Mm-hmm. Anyone else? If there are no questions, so I guess we can stop here. I will stop sharing my slides. If I can. Yep. All right. Thank you very much for attending my talk.
Great. Thanks, Sergey.
Thank you. Bye-bye.